Have you ever wondered what would happen if you crossed the point of no return? A place where gravity is so strong that even light can't escape. Tonight, we're diving into the most extreme objects in the universe: black holes. Not sci-fi portals, not cosmic vacuum cleaners, real, terrifying, beautiful consequences of physics pushed to the limit. Welcome to Eureka Lab. At Eureka Lab, we turn complex science into clear stories. In this episode, how black holes form, what an event horizon really is, what would happen if you fell into one, and the biggest mysteries scientists still can't solve. Let's begin where every black hole story starts, with a dying star. Stars live by a simple deal with physics. Inside, nuclear fusion pushes outward. Outside, gravity pulls inward. As long as those forces balance, the star shines. But when a very massive star, at least about 20 times the mass of our Sun, runs out of fuel, fusion stops. Gravity wins. The core collapses in on itself. If the collapsing core is heavy enough, there is no known force that can hold it up. It keeps shrinking, crushing matter into a region so dense that space and time themselves are dramatically warped. The result is a black hole. From the outside, we don't see a hole in the sci-fi sense. We see its effect on nearby stars, on gas, on light itself. A black hole is not an object in the usual way. It's a region of space-time where gravity is so intense that nothing can escape once it gets too close. Surrounding that region is a critical boundary called the event horizon. You can think of it like this. Outside the event horizon, escape is at least in theory possible. At the horizon, you would need to move faster than light to get out. And since nothing can outrun light, crossing that surface means you are committed. No turning back. Inside, all paths lead inward. Every future you could have ends at the center. Myth 1. Black holes suck everything in. Wrong. If our Sun were magically replaced by a black hole of the same mass, Earth would keep orbiting almost exactly the same way, just in the dark. From far away, a black hole's gravity is just like any other object of equal mass. Myth 2. They are wormholes or portals. As far as our best physics says, no evidence. Real black holes are extreme, but boringly consistent with Einstein's equations. That brings us to the fun question. What if you fall in? Imagine you're falling feet first toward a black hole. Gravity pulls stronger on your feet than on your head. That difference stretches you out. This is the beautifully horrifying process called spaghettification. For a small black hole, this happens well before you reach the horizon. You'd be torn apart by tidal forces in a fraction of a second. For a supermassive black hole, like the ones at the centers of galaxies, something stranger happens. At the event horizon, tidal forces can actually be mild. You might not feel anything special as you cross the boundary, not realizing that, from the universe's point of view, there is no path back. Closer to the center, however, physics goes completely off the rails. At the core of our equations lies the singularity, a point of infinite density where our current understanding of space, time, and matter simply breaks down. Is that singularity real, or just a sign that our math is incomplete? That's one of the biggest open questions in modern physics. We know of at least 3 main kinds of black holes. Stellar mass black holes, a few to tens of times the mass of our Sun, form from collapsing stars. Supermassive black holes, millions or billions of solar masses, sitting in the centers of galaxies, including our own Milky Way. Intermediate mass candidates, in-between monsters we're still trying to confirm. Almost every large galaxy we've observed seems to hide a supermassive black hole at its core. The one at the center of the Milky Way has about 4 million times the mass of the Sun. So, How do we know they're there if they're black? We can't see a black hole directly, but we can see what it does, orbits of nearby stars. When we track stars whipping around an apparently empty spot in space, we can calculate the mass of whatever is hiding there. Sometimes, the only explanation is a black hole. Accretion disks. Gas spiraling into a black hole heats up and glows, sometimes becoming brighter than an entire galaxy. That's how we get quasars, powered by supermassive black holes feeding in the early universe. Gravitational waves. When black holes collide, they send ripples through space-time itself. LIGO and Virgo have detected these signals, literally hearing black holes merge. Black hole images. In 2019 and 2022, the Event Horizon Telescope gave us images of the shadows of two supermassive black holes in galaxy M87 and in our own Milky Way. We're not seeing the black hole directly, we're seeing its silhouette against the glowing gas behind it. Step by step, the invisible is becoming measurable. For all we've learned, black holes are still trolling our understanding of reality. Three huge puzzles. The singularity problem. Our equations predict infinite density at the center. Infinity usually means you need better physics. A future theory of quantum gravity may replace the singularity with something deeper. The information paradox. If things fall in and never come out, does the information about them vanish from the universe? Stephen Hawking showed that black holes should slowly evaporate via Hawking radiation. If they disappear completely, what happens to the information? Many physicists now think the information must somehow be encoded at the horizon or in the radiation, but how exactly is still under debate. Their role in the universe. Did supermassive black holes help shape galaxies? Do they power the most extreme objects we see in the cosmos? And can studying them finally unify quantum mechanics and gravity? Black holes started as a wild idea on paper. Now they're a laboratory for the deepest questions in physics. So, what have we learned? Black holes are not magic holes in space. They are what happens when gravity wins completely. They bend light, trap time, stretch matter, and challenge the laws we thought we understood. And somehow, the universe is full of them. If you enjoyed this journey inside a black hole and want more clear, no-nonsense science explained in under 15 minutes, hit subscribe, turn on notifications, and share this video with someone who still thinks black holes suck everything in. This is Eureka Lab. See you in the next chapter of the universe.